is a chemical reaction which is proceeding in both directions at the same rate. So, of course, for an equilibrium you have, actually I will use a specific example. In fact, I might as well use the Haber process. Hydrogen and nitrogen in reaction producing ammonia, the Haber process Fritz Haber developed in the 20th century. And these were gaseous, and an equilibrium is dynamic. It's dynamic because the reaction is proceeding in both directions at the same rate. And that's at the point of equilibrium. Yes? Okay. Now, I'm going to go through this because I just want you to understand the principle. If you understand the principle, then everything else seems to slot much better into place. Okay. If I take some hydrogen and some nitrogen, in the presence of a iron catalyst, of course, don't forget, at 450 degrees C, approximately 200 atmospheres actually, Haber process plants to produce ammonia are run into quite different conditions all the way around the world. It depends on lots of things, but you know that's an average. 450 degrees C, 200 atmospheres, and those conditions are very, very important. They're very specific to that equilibrium. Why? Well, because we have to think about the position of equilibrium, and of course we also have to think about the rate of attainment of the equilibrium. And those are different things. So the point at which a reaction is in equilibrium is when the reaction is going in both directions at the same rate. Okay. Now, if I take some hydrogen and some nitrogen and I put them in a pot, they don't instantly form an equilibrium. They start to react, and when they first start to react, you have obviously nitrogen and hydrogen reacting together, and they form ammonia. So at the very beginning, the reaction only, of course, goes in one direction, doesn't it? If you've only got nitrogen and hydrogen, the only reaction which can happen is that it goes in this direction. Okay, so that's what happens at the very start. As soon as you start to get some ammonia formed, some of that ammonia is going to break up and go back the other way, because that's the nature of reactions which can reach equilibrium. They go in both directions. So to start with, you're going to have it going in this direction a lot, and in this direction only a little bit. And so you end up with a situation whereby one reaction is much, much quicker than the other. But after a while, as this reaction in the forward direction slows down, and the reaction in the reverse direction speeds up, you reach a point at which the reactions are going at the same rate. And that is the point of equilibrium. Okay. Now when it's doing that, all the other stuff, that's how long it takes to reach equilibrium. Now some equilibria reach equilibrium very quickly. And I can think of a good example of an equilibrium which does tend to reach equilibrium quite quickly, and that is if you open a can of Coke, okay, or a bottle of fizzy pop, or a bottle of beer. You pop the top open, and immediately you get a fizz. And the fizz is because you've changed the conditions of the equilibrium. And what you've done is you've taken the carbon dioxide out of the atmosphere at the top of your bottle or your can or your whatever, and you've taken that carbon dioxide out, and so you've reduced the concentration of carbon dioxide dramatically in the atmosphere, which means that all the carbon dioxide that's dissolved in the solution rushes out to replace that lost carbon dioxide in the atmosphere, because Le Chatelier's principle says that that an equilibrium will oppose any changes that you introduce. You need to scribble that down. Le Chatelier's principle says that an equilibrium will oppose any changes that you introduce. So what you have to the way you have to think about it is that if you increase the temperature, the equilibrium will decrease the temperature. If you drop the pressure, the equilibrium will increase the pressure. And we'll talk about why in a second. Okay. So, opening a can of Coca-Cola is a good example of a reaction in which the equilibrium shifts very rapidly. And it's a good example of a reaction in which the equilibrium takes a very long time to change, or it takes a very long time to get to equilibrium is an esterification reaction. If I take some ethanol and some ethanoic acid, and I put them together in a beaker, they won't reach equilibrium until about a week has passed. Okay, so the reaction is quite slow to get to equilibrium. Is everyone happy with that? Okay, good. Now, the key thing is that the speed at which something takes to get to equilibrium is of different consideration to the percentage that you have of yield, the percentage yield in the equilibrium mixture, and that's a term you need to use. So the percentage yield in the equilibrium mixture is basically how much you actually get of your product. In this case, ammonia, you tend to get a very low percentage yield for ammonia in the Haber process, even under these conditions. Now, why is 200 atmospheres used? Well, again, I know I'm talking about the Haber process, having said I wouldn't, but the reason I'm doing it is to talk about Le Chatelier's principle, which you do need to understand. So why is 200 atmospheres used? Well, it's used because Le Chatelier's principle says the equilibrium will shift to oppose the change you introduce. 200 atmospheres is 200 times atmospheric pressure. Okay, you'd have to go down a long, long way in the ocean to experience those sorts of pressures. 200 times the atmospheric pressure we're in. And why do they do that? Well, they do that because on the left-hand side there are 4 moles of gas, and on the right-hand side there are 2 moles of gas. So as you increase the pressure, the equilibrium will shift to the right-hand side because that is the side which will reduce the pressure. Now, the reason it does that is actually not to reduce the pressure, but I'm not going to go into that in great detail. It does it because it wants to. Because it wants to. You know what I'm saying? It doesn't have. It's not sentient. Okay. It does that. The reason that happens is because there is a ratio of concentrations in the mixture which is always the same. Okay. It's the ratio of concentrations that stays the same, and that's where the equilibrium constant comes in. The equilibrium constant is the ratio of concentrations. So, as a rule of thumb, we remember that Le Chatelier's principle is such that if you change the conditions, the equilibrium shifts to oppose that change. It can't cancel it out, by the way. If you start with an atmospheric pressure and you whack it up to 200 atmospheres, the equilibrium cannot cancel it out and bring it back down to 1 atmosphere again. But if I were able to do this and look at it, what I could do is I could start at 1 atmosphere, whack the pressure up to 200 atmospheres in a fraction of a second. Just imagine I could do that. And then I would find that the equilibrium would shift and the pressure would drop back down again. It would drop back down, maybe to 180 atmospheres. So the equilibrium will oppose the change. Do you see what I mean? Because by increasing the pressure, I force a change on the ratio of the mixture, and I produce more of this. And what we do is we use the terminology, we say that the equilibrium, by increasing the pressure, the equilibrium shifts to the left. No, it doesn't. It shifts to the right. And that increases the yield of product. Okay. Now, if you're all happy with those terms, we'll move on. You all happy with that? Okay. Now, Le Chatelier's principle doesn't just apply to pressure, it applies to concentration. Well, in fact, Le Chatelier's principle is all about concentration. So if I increase the concentration of a nitrogen, then I will find that the equilibrium will shift to the right to produce more ammonia, because it will drop the concentration of nitrogen. Okay. If I increase the concentration of ammonia, the equilibrium will shift to the left. Okay. So when they're making ammonia, for example, what they do is that they drop the temperature in the vessel with the ammonia, and the ammonia condenses out at minus 17 degrees centigrade, and the ammonia runs off. And as the ammonia runs off, that encourages the equilibrium to shift to the right again. So it's a nice, clever trick. Getting the ammonia away means that the equilibrium is constantly shifting to the right.
Does the equilibrium shift kind of actively to change, to cancel out the concentration change, or is it just the result of kinetics? Is it doing it because it reduces concentration, or is it just...
It's a result of thermodynamics. It's a result of thermodynamics. But we'll leave it at that for the moment. Okay, so that's that. Now, Le Chatelier's principle, of course, also applies to temperature. So, what we find is, again, it all comes down to thermodynamics, is if we increase the temperature, the equilibrium will shift to decrease the temperature. So, 450 degrees C, well, actually, that's not very high. Why? Because that's an exothermic reaction. And if you wax the temperature up to 2000 degrees centigrade, then the equilibrium is going to favour the left-hand direction, because that's the endothermic direction. Yes? Do you remember all this? Good, okay. So therefore, that's important to remember too. Now, what we I'm going to leave Haber and contact, except I've already talked about Haber already.